Hi, this is Mr. Wu, and welcome again to Disney Park Math. In episode 7, I'll talk about potential and kinetic energy, featuring again the ride Expedition Everest. Now, if you haven't viewed the previous episode yet, I would recommend doing that just to give you a better idea about the ride. So let's head on over again to Disney's Animal Kingdom in Orlando, Florida, and look at Expedition Everest. Here again is the ride. An example of what we talked about in the last episode of that forest perspective, making those smaller features up on top to make the ride look taller than it really is. Okay, let's talk about potential energy and kinetic energy using what I'm calling the energy equation, and this is how it works. These are the basic principles. It can go like this. So what goes up must come down. That sort of makes sense as far as the roller coaster. The work going up equals the ride coming down. So the more work going up, that energy converts to the ride coming down. And energy stored equals the energy released. So the more energy you store, the more energy is released in the ride. So a roller coaster's lift does work against gravity, and work in physics is defined as force times distance to bring the train up a hill, which will be of height h. So all roller coasters, you notice, or most of them do, have some sort of a lift to bring that train up before the ride goes down. In a previous episode, we learned about force, and force is equal to mass times acceleration. That's Newton's second law, which in the case of gravity then is just mass times g, the gravitational constant of acceleration. So mathematically, this work that we're talking about against gravity, which we also call potential energy, is equal to mass times g times h. We just say mgh. So let's see what this looks like on a ride. So here is our lift. There we go, we're going up. So PE, or the potential energy, is increasing proportionally to the height. The higher it goes up, the more potential energy. Okay, now let's talk about kinetic energy. So ideally, all of this potential energy can be converted to motion or kinetic energy as the train accelerates down the track as it goes into motion. Mathematically, kinetic energy is equal to 1/2 mass times velocity squared. That comes from physics. So our energy equation then becomes potential energy, or mgh, is equal to 1/2 mv squared, assuming all that potential energy can be converted. In the real world, of course, we are working in the real world, kinetic energy is reduced by factors such as friction and wind resistance. So actually not all of the energy is quite available. Some of it's going to be lost to things like friction and wind resistance. Also to note, real-world roller coasters such as Expedition Everest usually use a series of lifts, hills, or even boosters to store, release, or add energy to the ride. If you remember California Screamin', a launch is actually another way you can add energy to the ride. And it's this sort of back and forth of potential and kinetic energy, which makes the ride not only interesting, but thrilling as well. So let's look again at our picture. Again, here is our potential energy going up the lift. Now coming down in a simplified version. Here we are going down. Now as we go down, obviously the train accelerates and picks up speed. So the potential energy is going to decrease because the height, of course, is going down, one way to look at it. And that kinetic energy is going to increase because the velocity is increasing. So it's a definite play between the two, and ideally it's all converted, but there's going to be some losses to things like friction and wind resistance. So a simplified picture of what you see in most roller coasters. This is real basic roller coaster physics here. So let's again look at our ride view. What I want you to look at here is look out for those lifts and hills. Notice not just one lift or hill, but a series, and think about that play between potential and kinetic energy. Okay, and now we're going up the lift, increasing potential energy. Okay, going down a short hill, picking up speed, kinetic energy. Down. There's a lot of ups and downs. big lift where we really gain a lot of that height or H. We get a lot of potential energy here, which of course, as you remember, we'll see as the ride plays out. Alright, now we're ready for some problem solving. So, the Expedition Everest ride, as we learned in the previous episode, climbs to a maximum height of 112 feet. So that is the height or H. So, assuming all potential energy, which is mgh, can be converted to kinetic energy, which is 1/2 mv squared, what is the theoretical maximum velocity of the train? Okay, so some mathematics to work out there. Hint, think about the energy equation here. If mgh is equal to 1/2 mv squared, think about solving this equation for v, or velocity, in order to work that out. Okay, go ahead and pause here and work that out and see what you get on the next slide. Okay, did you work out a possible solution? So let's see what this might look like, right? A little more involved here. Okay, so let's get my pen. Okay, here is our energy equation. mgh, which is potential energy, ideally converts to kinetic energy, which is 1/2 mv squared. We want to know what that maximum theoretical velocity is. Okay, so we're going to want to solve this equation for v. Before we do it, let's simplify it. Notice that there is an m on both sides. Well, we can actually divide those out and cancel them out. And 1/2 v squared is just v squared over 2. So our equation becomes gh is equal to v squared over 2. As you might have remembered from physics, not that mass doesn't matter. In fact, it does relate to energy, but it doesn't actually affect the velocity. If you remember, in a vacuum, if you had to drop objects of different masses, they actually fall at the same velocity. They both are affected by gravity in the same way. Okay? So in an ideal world, of course. So let's solve this. So if gh is equal to v squared over 2, multiply both sides by 2. V squared is equal to 2 times g times h. Now we want to solve for v. So we're going to take the square root of both sides. So v then is equal to the square root of 2gh. Now let's plug in what we know. Okay, so g, we're working in feet. So the acceleration due to gravity is 32 feet per second squared. The height of the ride is 112 feet. Substitute those in. Multiply these out first, and then take the square root, and we get 84.7 feet per second. So that is the maximum theoretical velocity in feet per second. Of course, we're going to be interested in miles per hour, so let's do some dimensional analysis here. 84.7 feet per second. There's 50 to 80 feet in a mile, so these cancel out. Alright, now where's our miles? Now there are 3,600 seconds in an hour, 60 times 60. So these cancel out. And we're left with miles per hour. So complete the calculation there. And we get about 57.8 miles per hour. That's pretty reasonable for a roller coaster, so we know we're right in the ballpark here. So then, we can say the theoretical maximum velocity of an Expedition Everest train is about 57.8 miles per hour. Now, interestingly, the actual maximum speed of Expedition Everest is reported to be about 50 miles per hour. So that's quite reasonable. And in fact, we would expect it to be a little less, because remember, in an ideal world, not all of that potential energy is going to be able to be converted to kinetic energy. And of course, there's some different aspects of the track and design too that are going to affect that speed. Alright, thanks for watching.